So,
just a second. Let me for the video and everything. So it is a pleasure to introduce the last speaker of our conference on motifs in generalized geometry, Professor Ludmil Katzarkov from the University of Miami, and he will be speaking about Brauer Severi varieties.
Yeah, thank you very much. So basically, the reason for this talk is to explain why I've been pushing this with Alino and Leonardo and with Ernesto. So the story is there are two stories which on first side have very little in common, but if you look a little bit deeper, you see some commonalities. And so let's start with X symplectic manifold. And so let's say that we have a symplectic form, which is integral. And in this situation, the geometry of this symplectic manifold is very much similar to what we know in algebraic geometry. So, in particular, we can consider some version of sections of line bundles. So we take a line bundle L. There's the first charge class of it is equal to this. And so these symplectic manifolds have almost complex structure, so this is just a complex line bundle. But as Donaldson has shown, one can actually pretty much imitate the homomorphic section theory. So for k big enough, the bundle KL is asymptotically homomorphic sections. So these are sections for which the bar of them is not 0, but it's becoming 0 when k becomes very big. So this is infinity norm. So the good thing about this is that you have a lot of them, and then this kind of sections have some transversality properties, as Donaldson has shown. So the point is that actually you can use this section to imitate classical algebraic geometry, and so the theorem is that every symplectic manifold, you actually map from X to P2 given by these sections, which are asymptotically homomorphic. And so this map, let's, I mean, it's true in any dimensions, actually, in any dimension. But let's put just simplicity that the dimension of X or R is equal to 4. And so this is a finite map. And this map has a ramification.
Ludmil, what, there's some initial acronym on top of the map.
Yeah?
Yeah.
You took, how do you map to P2? You choose 3 homomorphic sections, and here you choose 3 asymptotically homomorphic sections. And so this is dimension 4 case of really finite covering. And so this covering is ramified over a curve. So which has the following characteristic. So it has finitely many nodes, cusps, and so pretty much behave like the curves that you get from generic projection in algebraic geometry. But it has also something which is called negative nodes. Which means that the local intersection form gets negative determinant. So this doesn't happen in the homomorphic situation. So now I don't know if these negative nodes can be actually removed. It could be that they don't, that you can choose the sections in a way that there are no negative nodes. Or if you cannot do that, that would be an indication of a strong invariant, but that's not known. So what is true that basically what we have here, we have a projection to P2, and then in the four-dimensional case, this is a finite covering. With a curve of ramification, homomorphic curve in P2 outside this points where you have cusps, nodes, and negative nodes. And so what is true here is that you can associate with this two group theoretic invariants. So one of them is representation mu from the fundamental group of fundamental group of the complement to this Riemann surface to the symmetry group. And then, so there is another representation. So the world expert on that sits in the back of the room. This is so-called braid factorization. So it's a little bit different because there are no negative nodes in the complex world. But still, what you could do is to take this P2 and so here is your curve. So there are nodes, cusps, and ramification points, and negative nodes maybe. And you can project from a line, sorry, from a point outside this curve, or if you like, blow up this point and get F1. And then
Sorry, what that's K.
SK is the symmetric group. So this is just the color.
The K is the number of sheets?
No. So this happens only after you should big enough. So I mean, that should probably write NK. So, and what you have here is a projection over Q1. And so this projection has some certain number of ramification points, which you remove. Then nodes. I didn't bother to draw them, and then cusps. And so after you remove all this, so basically you have a fiber which is Q1 minus number of points, which is the degree of the curve. And you have monodromy at exactly at these points where these points come together. And so in such a way, out of this data associated with the curve, you have a representation rho from phi 1 Q1 minus these points into the group of automorphisms of the fiber, which will be the braid group of decay strains. So basically, the theorem is that this data for k big enough completely recover X. So in other words, you can record all information for this symplectic manifold in these two group representations. One of them is representation in the symmetric group, and the other is the representation of the braid group.
Up to symplectomorphism?
Yes. So now you have this theorem which actually can be extended to higher dimensions. I mean, so it won't be completely recovered, but it's certainly a symplectic invariant. And so now what remains to be done is to find some examples where you can actually calculate something. And that, as usual, is never easy. So, you know, even if you put some estimate on K, at the end of the day, you end up with comparing two words in the braid group, modulo some funny equivalences, and that is not a very pleasant exercise. So the first thing to try to do is to look at some invariants which are consequence of the this huge work in the braid group that you want to study, but are easier to compute. So now let me say that in a way this is opposite to the, but still certainly related to what parallel to our conference, Maxime is talking about in Paris these days. So there we want to study algebraic geometry, questions of non-rationality, by imposing the A side, in other words, Gromov-Witten invariance, into the B side, the derived category, but without really computing derived categories. So just using Gromov-Witten theory to split the homology in direct sum of homology of atoms. So now what we are going to try to do is to do the same thing, but in a way to enhance the Gromov-Witten theory by some algebra geometric homotopy theory structures which allow us to distinguish symplectic manifolds when they actually have the same Gromov-Witten theory. And so that's the question, indeed. So can you find two symplectic manifolds, x1 and x2, such that they are simply connected, they are homeomorphic to each other, but not symplectomorphic. So, sorry, I apologize. I said something. You have the same Gromov-Witten invariance, but are not symplectomorphic. We can ask the same question with Witten. It's like the same. So I must say that the answer of this question is not known. So it is a bit hard. I'll try to demonstrate this on some examples. So the examples that were suggested in that direction belong to Donaldson. Actually, certainly are influenced by ideas of Milner. So they appear one way or another in Philip Stokes. These are the well-known Horikawa surfaces. So obviously they come in families, and I'll do one of them. They're infinite family, infinite series. So we start with X1 being two-sheeted covering of Q1 cross Q1, ramified in a 612 curve. And then the second is two-sheeted covering of F6. This is the Katzarkov surface F6.
Ramified? What is it ramified?
The first one or second one?
X1.
First one's a 6-2 curve.
612.
612.
So in fact, to make Leonardo and Milna happy, let me draw them. So they have this all right, so we have 12 of this.
The curve is just a bunch of lines. You're saying the curve is just a bunch of lines.
Yeah, no, but yeah, indeed, you can degenerate a bunch of lines. Yeah, so someone who loves toric geometry, and so you need to be careful what to do with the cusps and nodes here. And here the ramification curve is of this form. I mean, so you can think of this like two-sheet covering ramified in this 612 curve, which I didn't draw, and this is F6 here, another toric surface. And so again, what you can do is really just draw this curve as lines and then consider the covering, and then we're going to get some very degenerated covering. But the geometry behind all this is the following. So 612 curve, obviously this is a very ample divisor on P1 plus P1, so generic curve is as smooth as you can imagine, and there all these curves are generic ones are connected by Bertini theorem. So here, because of that, so the curve is going to consist of something which is really very, very smooth and irreducible, but there is another component which doesn't intersect this one, since these two don't intersect. So, so this curve is connected, this is disconnected, and the one of the surfaces is obtained from another by a surgery, which is called the Ludmil surgery. Sorry. So Ludmil actually is alive. It's in Switzerland.
What is that?
Ludmil surgery.
So, what is it?
So you take a so this covering has a Lagrangian toroid in it, and so you pick up this Lagrangian toroid and you perform this surgery around this Lagrangian toric. So what's happening is that so we have locally this sheeted coloring coming from this, so it's a familiar hyperelliptic. Obviously, we have a pencil of hyperelliptic curve of genus 2. And so let's say that this is the generic curve. Those 6 points, which is the elliptic curve of genus 2, hyperelliptic curve of genus 2. And then, so locally, you choose a locally you choose a S1 and then another S1 in this direction. So that gives you a Lagrangian toric. And so once you perform the surgery around this Lagrangian toric, so what you are going to get is that these things kind of split and you have this component, and then so the rest splits, and so basically it's this surgery around chosen generic smooth fiber of this hyperelliptic vibration that gives you the fact that this curves, so that this Ultinger surgery produces this kind of these two curves, so the result is a disconnect. So I mean, this in order to properly see this, you need to do a lot of careful Kirby calculus. And it's done by Gomb, obviously, the only person now in the world who knows what that is. And his student Terry Poor. But it's a very long and careful paper published in Mathematics, how people from one to
So
another.
this is the symplectic, not
Yeah.
on one
Yeah.
side where they.
Wow. These are complex, these are very algebraic surfaces because, so you could ask if there are symplectic informations which are not algebraic, and if you're asking me this, I don't know that.
It's a long question. It's a very long question.
Most likely not, but we don't know. So I mean, there are these papers that Moshe is on and Fabrizio, where they show in some cases that this doesn't happen, but that's not the case. So in any case, so these are the examples, and what you want to try to do is to distinguish them, and so obviously you don't succeed. But I know this at the beginning, but so and the reason is because there are some things which you can easily compute.
These two are homeomorphic, right?
I mean, that's easy to check because by Friedman's theorem, I mean, which is believed to be true, not proven, but so, I mean, maybe artificial intelligence will help us. I don't know. It's a big team in England. I mean, actually, I don't know. So there are strong components like Stavros Berouffaridis. There's no counterexample. So, but it says that if you have the second homology being the same as well.
And how, sorry, you're gonna tell us something about the Gromov-Witten or
No,
is this
I won't go to Gromov-Witten. Let's say Cyber-Witten. These are services of general type. There's only one basic class. So, so these are homeomorphic. They have the same Gromov-Witten invariants, certainly simply connected. So what can you do is really try to use this technique of braid factorizations. And so you
This Ludiger surgery a priori generates a difference in plastic output, right? Or
I mean, I don't know a single case. Where, I apologize, I lied to you. So there is a paper that I wrote with Norton and Uru where they do generate different non-superimposable things, yes. But not, in this case, I don't know. So, so what we are going to do is we consider this projections to P2, which I mentioned. And so now we are getting close to what, but not quite, to what Ernest, sorry, yeah, and Lino and Leonardo were talking about. So we consider these projections to P2 minus curve. And so we do know that all the information is there. So if we compute this works in the braid group, so everything is the same. So what you want to compare is these two works in the braid group. So I said that's hard, but instead of this, what you can compute is the fundamental group of P2 minus this curve. And so that is computable. But as theorem of Donaldson, Uru, Yotov, and myself shows, and it's much more general result than just this Polycard surfaces. For all cases, these are the same. So that doesn't help. So in fact, the way to compute this is pretty much depends on the intersection theory of NH2, as the theorem shows. So pretty much we cannot move away from them being homeomorphic. So now what is needed here is some kind of invariant which is not as simple as the fundamental group of the complement, but it's not as complicated as the work in the braid group, which we want to compare to a crazy equivalent. So, and that seems to be something that relates to the story which was discussed by Lino and Leonardo, and so I'll try to make this quick connection now. You want to start?
No. You want to know if those two braid representations are isomorphic, right?
Yeah.
And that's just hard to.
Yeah,
You can write them down, but it's hard to know if they're isomorphic.
Yeah, with the word problem in group 2, then
Is there some kind of estimate on K, like for which minimal K you need to check it?
but the issue is that even if K is 1, that won't help. That's the problem. But as an overall algebraic surface, K is worth 5, and 5K gives embedding.
But a computer might be able to check that.
I mean, this is an artificial intelligence problem. So, I mean, machine learning problem, yes. I mean, I'm surprised that nature is not filled up with papers of this subject. Empty, of course. But in any case, so let's see what were the things that we learned from Lino and Leonardo from this perspective. So they were considering S1 cross S7 or S1 cross sigma 7. So these were the Milnor exotic spheres, and all these manifolds they have rather interesting structure. So they all map to. So first of all, you can actually put additional ZL action or direction of S1, and so they are all obtained from one to another by these surgeries, depending on two parameters, which were called generalized log transforms in the corresponding talks. And so the result of the generalized log transforms were P2s minus curves. In other words, these were vibrations over P2 minus curves. See, what was it? 6K minus 2? 1. Minus 1. And so this K moves from 1 to 28, and so the L is the other parameter depending on the zero action that we can impose there. So we are in a rather similar situation. So we have surgery here, which produces two different curves in P2, and we are trying to find a way to distinguish this curve by some topological or more involved techniques. So now, so we do know quite a bit about these curves, and so certainly we do know that dB sync associated with these curves are product of sorry, in terms of product of this categories. And so more or less, this gives you a different way to think about the
Same, yeah, same. Category of singularities.
yes. Yeah. So to think in a different way about the smooth invariance of these manifolds, just multiply by S1. And then, of course, if you get the action of S over S1 involved, you will get similar twists, or if you like, twisted shifts associated with this categories of singularities. But the interesting part here is what can you say about P2 of minus C6K minus 1, but in this case, don't consider DP, but actually Fukaya side or rough category associated with this. So now the conjecture that I want to pose here is that so I'll be rather vague here. So the topological modular form associated with this, sorry, I forgot that the fiber of this map are going to very well understood. And so for the first one, this is just the Hopf surface, and then they just become length spaces. Process one. And of course, over the curve, there are complications. And so the statement that I wanted to make here, the associated, the topological modular form associated with this manifolds actually produces invariant of this Fukaya category. Now, so I don't know enough about logical modular form, and so there are bigger experts than me on this. But not so careful reading of the paper by the Congress paper by Mike Hopkins, where some of these, in this case, are computed. Actually, suggests to me that might be the case. So another paper of Seidel suggests that if you know that these two are different, then these are not simply small. That was not from them.
Just to understand a little bit the statement that we are considering. Here you just say if we apply the extraordinary cohomology theory TMN to these two spaces.
Oh, yes, yes. And so I claim that actually it measures the geometry of the P2 minus the curve. Actually, there is a statement with that in Hopf system.
So you mean you think about this sort of by
Yeah. So we imitate what we know in the symplectic situation. Just in this case, we have complex manifolds. These are all complex manifolds, which happen to have these projections to P2 minus the curve. And so we claim that it's the geometry of P2 minus the curve that recovers the topology of this, but actually there is more, as Hopkins indicated. And so this saves you the trouble of going to the plate factorizations, but this extraordinary theory, which are hard to compute, one must say, might be the hope, but they look more computable than the words in the breakthrough, that's for sure. Well, I don't know. Ernesto seems skeptical.
Well, typically these calculations with DMF are very, very hard because the spectral sequence is extremely.
But there are techniques.
Yeah. You have the model forms, and then you have the spectral sequence, and you can try, maybe even on the computer.
But with pre-factorization, I don't think that even machine learning is going to help. Well.
So, present, do you mean present of the mirror?
No. This is category of timbers that you can associate with this vibration of Q1s minus points. So this is a pencil of Q1s, and then you can associate with it with that category.
What was this? What was the statement about the category of singularity of C? What was?
I mean, didn't you speak about this?
Yeah. I just mentioned because you have like isomorphism of triangulated categories because the singularity defines left vibration, and then you can consider.
I see. So you look at the CK. CK is there inside. I see.
No, this manifold is dimensional, so there's a much more than just if they are diffeomorphic or not. I mean, so there's much more theory involved there, and that's what we are in a way trying to employ here. But if indeed we can actually build some kind of extraordinary homology theory invariant for the category from here, so then one can try to go back and look at this thing that you get from Katzarkov category and try to compare the topology that you get from the projections from to CP2 out of this. So I mean, once again, it could be that these hopes are a little bit too crazy, and also it could be that actually they are the same. so just happens that these numbers are the same, and so. But the situation is rather parallel. I mean, so you have this Luttinger surgery, as I mentioned in the case of Kurikawa surfaces. You have these surgeries that is generalized of transform that you have here, and my understanding of what Mike's writing there that this generalized slope transform actually leads to change of the coefficients in the topological form. And, if that's the case, you have some hope. All right, so that's different point of view.